Hello everyone, and welcome to this recorded session for Topic Radio Digital Modulation. My aim today is to provide a comprehensive overview of how digital signals are prepared and transmitted wirelessly. Please feel free to pause and rewatch any section as needed, and I'll provide details on how to ask questions at the end. Before we dive into the how, let's address the fundamental why. Why do we modulate digital signals? Raw digital pulses, what we call baseband signals, are generally not transmitted in their original form. Think of them as raw data that needs a suitable vehicle or carrier to travel across a given channel. This modulation process makes digital signals suitable for transmission through free space, using an analog carrier. We'll explore three primary techniques today: amplitude shift keying, frequency shift keying, and phase shift keying. The core concept of radio digital modulation is quite similar to its analog counterpart. The modulating signal, which in our case is a digital signal, a sequence of zeros and ones, will vary a characteristic of the carrier signal, either its amplitude, frequency, or phase. Here's a high-level block diagram illustrating a typical digital transmission system. We start with digital data, which often undergoes a process called line coding, using techniques like RZ and RZ or AMI to prepare the pulses for modulation. This prepared digital data is then used to modulate a carrier signal. The modulator's crucial task is to shift the baseband digital signal spectrum to a higher frequency, typically centered around the carrier signal's frequency. After transmission through the analog channel, the signal is demodulated at the receiver, then decoded, allowing us to recover our original digital data. Our first technique is amplitude shift keying, or ASK. In ASK, the digital signal directly switches the carrier amplitude between a high and a low state. It's so straightforward that it's also commonly called on-off keying, or OK, and sometimes even interrupted continuous wave. Essentially, a digital one might turn the carrier on at a certain amplitude, and a zero turns it off, or to a very low amplitude. The string of digital pulses directly dictates this amplitude change in the carrier signal. To generate an ASK signal, the simplest method is to use a multiplier. We input our modulating digital signal V sub M, T, and multiply it with our carrier signal V sub C, T, to produce the ASK signal V sub ASK T. Mathematically, our modulating signal, if it's a unipolar pulse train, can be represented by a Fourier series, as shown here. Our carrier is a simple cosine wave. When these are multiplied, the resulting V sub ASK T equation clearly demonstrates how the carrier's amplitude is modulated by the components of the digital signal. Understanding the frequency spectrum is crucial for any modulation technique. In the time domain, you can clearly see how the ASK signal's amplitude changes in response to the digital data. Now, let's transition to the frequency domain. The ASK spectrum shows components clustered around the carrier frequency, FC. If we consider up to the first 5 harmonics of the modulating signal, the bandwidth of ASK is approximated as 5 times FM. However, for an unperiodic digital signal, the bandwidth of ASK simplifies to simply equal the bit rate, FB, where FB is twice FM. To recap, ASK signals can be generated using a multiplier, which we've just seen, or through a simple on and off switch controlled by the digital data. On the receiving end, we have 2 main options for demodulation: an envelope detector, which is simpler but less robust to noise, or a coherent detector, which requires a synchronized carrier signal at the receiver for more accurate demodulation. In digital communication systems, noise and errors are inevitable. We measure these using the bit error rate, or BER. BER quantifies the proportion of bits that are incorrectly received compared to what was sent over a given time period. BER is significantly influenced by factors like the specific modulation technique used and the signal-to-noise ratio, often expressed as EB/no. Here, EB is the energy per bit, and no is the noise power spectrum density. For ASK, The theoretical probability of error, PE, is given by this formula involving the complementary error function, ERF. Next, we move to frequency shift keying, or FSK. Here, instead of varying the amplitude of the carrier, the digital signal shifts its frequency. A digital 1 might correspond to one distinct carrier frequency, say FC1, and a digital 0 to another, FC2. An interesting way to conceptualize FSK generation is by generating two separate ask waveforms, one for each frequency, and then adding them together using a summing amplifier. We can generate FSK in a couple of primary ways. One method, as previously mentioned, involves using the digital input to effectively switch between two different oscillators, generating two distinct frequencies. These are then combined. Another common and often more direct approach is to use a frequency-modulated oscillator or a voltage-controlled oscillator, VCO, where the digital input directly controls the output frequency, causing it to shift between FC1 and FC2. Let's look at the mathematical foundation for FSK. The baseband modulating signals, VM1T and VM2T, are complementary, meaning one is the inverse of the other. Each can be represented by a Fourier series. The FSK signal, VFSK-T, is then the sum of two distinct carrier waves, each multiplied by one of these baseband modulating signals. This clearly shows how the two carrier frequencies, omega C1 and omega C2, are selected based on the digital input. The bandwidth for an FSK signal is determined by the separation between the two frequencies and the characteristics of the modulating signal. If we consider up to the third harmonics, the bandwidth of FSK is approximately 6 FM. For unperiodic signals, the bandwidth is given by FB plus 2 delta F, where delta F is the frequency deviation between the two carrier frequencies. This generally indicates that FSK requires a somewhat larger bandwidth compared to ask for similar data rates. Here's a more detailed look at practical FSK generation methods. One approach uses two modulators, each taking one part of the data stream, one normal, one inverted, and modulating it with a specific carrier frequency, F1 or F2. These modulated signals are then combined in a summing amplifier to produce the FSK waveform. Alternatively, the voltage-controlled oscillator, VCO, is a very direct way. The digital data stream acts as the modulation input, directly switching the VCO's output frequency between FC1 and FC2 based on the 0 or 1 state of the digital signal. For FSK, we can use both unsynchronous and synchronous receivers. Let's first look at the unsynchronous FSK receiver. This design utilizes two bandpass filters, each specifically tuned to one of the two distinct FSK frequencies, omega C plus delta omega and omega C minus delta omega. The output from these filters determines which frequency was received, and a logic comparator then generates either a logic 1 or 0. The probability of error for an unsynchronous receiver is given by this formula, which involves an exponential decay dependent on the energy per bit, EB, and noise power spectrum density, NO. Remember, EB for FSK is ECT/2. Let's apply this to a practical example. Consider an unsynchronous FSK system operating at 10 MHz with a frequency deviation of 850 Hz and a bit rate of 110 bits per second. We are given the peak-to-peak carrier signal is 2V, and the noise power spectrum density is 1 × 10 to the power of -4 volts superscript 2/Hz. First, we calculate the peak carrier amplitude, EC, and the bit period, T. From these, we determine the energy per bit, EB. We also extract the noise power density, NO. Plugging these values into the PE formula for unsynchronous FSK, we arrive at a bit error rate of approximately 5.74 by 10 to the power of -6. Now, let's consider the synchronous or coherent FSK receiver. This method requires a synchronized local oscillator at the receiver that generates carrier signals at both omega C plus delta omega and omega C minus delta omega. The received FSK signal is multiplied by these local carriers. If, for instance, the received FSK signal is at omega C plus delta omega, the output after multiplication and filtering will predominantly be EC/2. Conversely, if the signal is at omega C minus delta omega, the output after the LPF will be minus EC/2. These positive or negative values then represent the output digital signal. The probability of error for a synchronous detector is generally lower, as shown by this formula, which again uses the complementary error function. Let's take the same FSK signal parameters from example 5.1 and apply them to a synchronous receiver. We use the same calculated EB and no values. Substituting these into the PE formula for a synchronous FSK receiver, we find the BER is approximately 9.5 times 10 to the power of minus 8. Now, let's compare this to the unsynchronous receiver's BER of 5.7 by 10 to the power of minus 6. This comparison clearly highlights that the synchronous receiver provides a significantly lower bit error rate, indicating a much more robust performance against noise. Finally, we come to phase shift keying, or PSK. In PSK, the phase of the carrier signal is shifted based on the digital input. For example, a digital 1 might set the carrier phase to 0 ring operator, while a digital 0 sets it to 180 ring operator. This means the signal literally flips its phase when the bit changes from 1 to 0. This fundamental phase shift is key to encoding the digital information. Similar to ASK, the bandwidth of PSK, specifically binary PSK or BPSK, is given by FB or twice FM. This indicates that PSK generally has a similar bandwidth requirement to ASK for the same data rate. The spectrum shows a suppressed carrier, with the energy primarily in the sidebands that carry the phase information. PSK can be generated in a couple of ways. One method uses a switch, where an inverter helps convert the binary 1 to a -1 signal. Both the 1 and -1 signals are then fed to the switch to produce the PSK output. Alternatively, a more common method involves a double-balanced modulator. Here, a unipolar to bipolar converter transforms the digital input, which then modulates the carrier, generating the PSK waveform. For accurate demodulation, a PSK receiver must employ a coherent detector, meaning it requires a synchronized local carrier. The advantages of PSK are noteworthy. It demonstrates good immunity to noise, it offers the same bandwidth efficiency as ASK, and it's scalable to multi-level modulation, which we'll discuss shortly. The probability of error for PSK is given by this formula, where EB is again the energy per bit and no is the noise power spectrum density. In general, PSK often achieves a lower BER compared to FSK or ASK under similar noise conditions. Let's revisit our ongoing example, using the same EB and no values from example 5.1, but this time calculating the BER for PSK. Substituting these values into the PSK-PE formula, we find the BER for PSK is an incredibly low 7.75 by 10 to the power of -12. Now, for quick comparison, synchronous FSK had a BER of 8 by 10 to the power of -8, and unsynchronous FSK had 5.7 by 10 to the power of -6. This comparison strikingly demonstrates PSK's superior performance in terms of error probability, making it a very robust modulation technique. To briefly summarize the 3 fundamental digital modulation techniques we've covered, ASK varies the amplitude of the carrier. FSK shifts the carrier frequency between 2 distinct values. PSK changes the phase of the carrier, typically between 0 ring operator and 180 ring operator for binary PSK. This table provides a concise visual overview of their behavior. Moving to a more advanced and widely used technique, we have quadrature phase shift keying, or QPSK. The key characteristic of QPSK is that one symbol now represents 2 bits, unlike the single bit per symbol in BPSK. This means for 4 different symbol combinations, 0, 0, 0, 1, 10, and 11. The phase will vary across 360 ring operator. Specifically, for QPSK, the phase shifts are typically 45 ring operator, 135 ring operator, 225 ring operator, and 315 ring operator. QPSK offers a significant advantage over simple BPSK due to its higher spectral efficiency, achieving 2 bits per second per hertz. It also commonly utilizes gray code for mapping bits to phases, which minimizes bit errors when a symbol is misinterpreted. Mathematically, each of the 4 QPSK signals is represented by a carrier with a specific phase shift, as shown here for the gray code mapping. The process of mapping is crucial. It separates the incoming bits into 2 orthogonal components, the in phase, or I, and the quadrature, or Q components. The general QPSK signal, SQPSK, T, can be expressed with the phase term depending on M, which represents the 4 different symbol states. The carrier phase effectively varies for every 2-bit periods, which is the duration of one QPSK symbol, TS equals 2TB. A powerful way to conceptualize QPSK is to view it as 2 independent BPSK systems operating in parallel, but with a crucial 90-ring operator phase shift between their carrier signals. The incoming serial data stream XT is first demultiplexed into 2 parallel streams. The even-numbered bits form the in-phase, I, channel, A1, T, and the odd-numbered bits form the quadrature, Q channel, A2T. Channel I is effectively a BPSK system with phases of 0-ring operator and 180-ring operator. Channel Q is another BPSK system, but its carrier is shifted by 90-ring operator, so its phases are 90-ring operator and 270-ring operator. When these 2 orthogonal BPSK signals are combined, they form the QPSK signal. The constellation diagram is an essential visual representation of a modulated signal. It displays the signal as a 2-dimensional scatter diagram in the complex plane at the symbol sampling instance. For QPSK, you'll see 4 distinct points. The angle of each point, measured counterclockwise from the horizontal axis, represents the phase shift of the carrier wave from a reference phase. The distance of a point from the origin represents a measure of the amplitude or power of the signal. It's also important to note that the QPSK spectrum is half the bandwidth of a BPSK signal for the same bit rate, another benefit of its increased spectral efficiency. Here are the block diagrams for a typical QPSK transmitter and its corresponding receiver. On the receiver side, after the initial QPSK input signal is received, a bandpass filter is used to reduce unwanted signals and noise. The filtered output is then processed to extract the I and Q signals, which are demodulated using synchronized cosine and sine carrier signals, respectively. Low-pass filters then remove any high-frequency components that result from the demodulation process. The outputs from the LPFs go to voltage comparators, which convert positive sample values to a logic 1 and negative values to a logic 0. Finally, these parallel binary signals are combined by a differential bit decoder or parallel to serial converter to reconstruct the original NRZ data output. The probability of error, or BER, for QPSK is given by this formula, which is the same form as for BPSK. It depends on the energy per bit, EB, and the noise power spectrum density, NO. In practical scenarios, BER is often considered in relation to the carrier-to-noise power ratio, C/N, at the receiver input. The relationship between EB/NO and C/N is given by this equation, where BW is the bandwidth for noise at the receiver and FB is the bit rate. This equation allows us to link the energy efficiency to the power efficiency of the system. Let's perform a very insightful comparison. The carrier-to-noise power, C/N, needed to transmit data at 120 megabits per second using both BPSK and QPSK, assuming a required BER of 10 to the power of -7. For BPSK, we first find that an EB/NO of approximately 13.5 is required to achieve the target BER. Since BPSK has a spectral efficiency of 1B/s/Hz, its required bandwidth is 120 MHz. Using the C/N relationship, we calculate the C/N for BPSK to be 13.5, which is about 11.3 dB. Now, for QPSK. Interestingly, for the same BER, QPSK also requires an EB/No of approximately 13.5. However, QPSK boasts a spectral efficiency of 2B/s/Hz. This means for the same bit rate, it only needs half the bandwidth, 60 MHz. When we calculate the C/N, we find it's 27.0, or approximately 14.3 dB. This comparison reveals that while QPSK is twice as spectrally efficient, it requires about 3 dB higher C/N than BPSK to achieve the same bit error rate. Beyond QPSK, we delve into M-ary phase shift keying. The M here refers to the number of distinct symbols or levels used in the modulation system. Common examples include 8 PSK, 16 PSK, 32 PSK, and 64 PSK. In an M-ary system, each symbol can represent multiple bits, following the fundamental relationship M equals 2N, where N is the number of bits per symbol. For instance, a 16-level system means each symbol can represent 4 bits. The trade-off is important. While increasing the number of levels allows for more data per symbol and higher spectral efficiency, it also results in more complex circuit designs and requires a higher C/N ratio for reliable communication. Table 5.2 provides a useful summary of the BER performance, spectral efficiency, and C/N requirements for various M-ary PSK systems, all targeting a BER of 10 to the power of -7. As you move from BPSK to 32 PSK, you can clearly see the increase in spectral efficiency, more bits per second per hertz. However, this comes at the cost of a significantly increasing C/N requirement in decibels. The fundamental principle is that an increase in energy per bit, EB, will invariably reduce the BER and thereby enhance the overall performance of the communication system. Finally, Figure 5.19 is a critical graph that visually summarizes the bit error rate performance across various digital modulation techniques as a function of EB/No. Studying these curves, we can conclude that for a given EB/No value, PSK generally offers the best performance, achieving the lowest BER. This is closely followed by FSK and then ASK. This visual comparison reinforces the theoretical advantages we've discussed for each modulation scheme. Thank you for watching this recorded presentation on radio digital modulation. I hope it has provided a clear and thorough understanding of these fundamental concepts. As this is a recorded session, if you have any questions, please don't hesitate to reach out by posting your questions on the group channel. I'll be happy to clarify any points. Thank you.